Welcome back to the Deep Dive, the place where we turned complex engineering specifications into, well, essential knowledge. Today, we are moving far, far beyond standard consumer reports. We're jumping straight into the true, ruggedized frontier of electrification.
We really are. We're trading the sleek, silent passenger EV for something
Yeah.
far more demanding, the P2 hybrid cement mixer truck.
Right, and when engineers talk about electrification challenges, this is what they mean: survival in truly hostile environments.
Exactly. Our sources today are drawn from a really comprehensive engineering spec report. It's essentially a blueprint for building the capability to develop a high-voltage connection system for this machine completely from scratch.
And the mission, as this report defines it, it's not just about small improvements. It's about engineering a zero-failure high-voltage system. I mean, the entire backbone wiring, connectors, junctions on a 24V 400V platform that has to survive a staggering 15,000 engine hours.
And 15,000 hours, you have to put that in perspective. That represents about a decade of hard commercial service. So this isn't just about moving power efficiently. It's about ensuring that whole power delivery system survives in what the specification bluntly calls the most chemically and physically brutal environment on the planet.
Wow. So you're basically building a system that lives inside a moving quarry and a chemical plant at the same time.
That's a perfect way to put it.
And the report makes it painfully clear from the get-go. Any engineering team starting this project has to immediately discard all their passenger car assumptions. If you design to a standard automotive spec, you are, and I'm quoting here, designing for guaranteed failure.
We need a completely different approach.
A radically different approach, absolutely. And the one outlined here is very much a professional consultancy-style guide to building that capability. It addresses power, economy, ISO 26262 safety, and this huge bucket of environmental adaptability. And to really understand how they get to that zero failure goal, we're going to follow the report's 6 sequential stages.
Okay, lay them out for us. First, we start with the rules, which are the regulations. Second, we look at the core sizing and material selection. Third, we manage all the electrical noise with the shield, that's EMC protection. Fourth, we deploy the armor, which is all about environmental adaptability. Fifth, we install the Guardian for functional safety. And then finally, we prove it all in the gauntlet, which is validation and testing.
All right, let's get started by laying down that regulatory foundation. Okay, let's unpack this. When you're designing a heavy-duty vehicle like this, the OEM has to plan for global sales. You're talking Europe, China, North America, Japan. The cost and, frankly, the complexity of stocking 4 different wiring harnesses would be astronomical. So the report mandates this strategy of the most stringent overlay.
And this is a really fundamental strategic decision. It's all about simplifying the bill of materials, the BEM, and just eliminating those regional design variations. You identify the single toughest requirement across all 4 major markets for every single component. It could be insulation thickness, contact plating, vibration resistance, anything. And then you design every version of the truck to meet that one single highest common denominator.
So you're over-engineering for some markets, but it pays off in simplicity.
It's a huge initial commitment to quality, yeah. It significantly exceeds the minimum legal compliance in any one region, but it saves you a world of pain down the line.
So if we look at those key regions, what are the specific burdens they place on the HV system design? Let's start with Europe. It sounds like their focus is on consequence mitigation.
It is. Europe focuses heavily on system-level safety. They use ECE R100, which is now in revision 3, and they couple that with ISO 6469. The major change that dramatically impacts the harness design is this mandatory requirement for addressing thermal propagation in the battery pack.
Thermal propagation. That sounds like a battery requirement. How does that impact the HV harness itself?
That's the key question. The principle is that the system has to give a 5-minute warning to the driver before a catastrophic failure, fire, and explosion occurs. But that warning system, that reporting infrastructure, it relies entirely on the harness.
I see. So the wire has to survive the event it's supposed to be reporting.
Exactly. The high-voltage communication line that connects to the battery management system, the BMS, it has to maintain its signal integrity even in the immediate high-temperature environment of a developing thermal event. If a fire starts to breach the initial barrier, the BMS needs that line to transmit the critical propagate warning signal. So that means the insulation and the jacketing for that specific communications cable have to be rated for extremely high short-term thermal excursions, well above normal operating temps, all to make sure that 5-minute window isn't lost because the cable itself melted.
That's a fascinating constraint. You're using a regulatory safety rule to dictate material selection on one specific wire run. Meanwhile, China, with standards like GBT and QCT 1067, they seem to approach this from a manufacturing control standpoint.
Yeah, China basically acts as the primary supply chain threshold,
Right.
which is critical since so many components are sourced there. QCT 1067 puts a heavy emphasis on mandatory material and type approval tests. We're talking insulation quality, flammability, IP rating, and all of that has to be performed and documented by the supplier before the part even ships. It takes the burden of initial validation off the OEM. It mandates that the supplier proves the material's robustness from the very start. If your supplier's data package doesn't meet QCT, it doesn't matter how good it is in theory. It's instantly rejected.
And then we move to North America, where the priorities shift a bit to crash resilience and just heavy-duty cycling.
Right. You have post-collision safety requirements like FMVSS 305, which is about making sure the HV harness avoids crush zones that could short out in a crash. But for this cement mixer, what's far more critical is the reliance on SAE J4555. That is the bedrock standard for heavy-duty trucks. It provides requirements for continuous duty cycles, chemical exposure, vibration, temperature extremes, stuff that's just completely absent in passenger car standards like US car. J4455 ensures the design accounts for the relentless pounding a Class 8 truck takes.
Okay, so now we get to the core challenge. Even if you designed the toughest overlay of all those standards, the report says there are these critical environmental threats, these law's blind spots, that the engineer still has to proactively deal with.
And this is where standard compliance ends and real specialized engineering begins. The first blind spot is simple exposure, no clean installation zone assumption. Unlike in most passenger cars where the HV system is sealed away inside the frame or cabin, on a mixer truck, every single component, even deep inside the chassis, is exposed to filth, spray, and impact. There's no safe space.
And the chemical vulnerability is uniquely severe because it's not just one thing, it's these alternating attacks.
It's the single biggest threat to the insulation material. We call it the acid-alkali alternation. Cement slurry itself is a strong alkali. It can reach a pH of 12 or 13. This causes hydrolysis, the chemical breakdown of many polymers over time. But then to clean the cured cement off, operators use strong cleaning agents, often diluted hydrochloric acid, which can push the pH below 3.
So you're swinging from one extreme of the pH scale to the other over and over again.
Constantly. And standard automotive tests might check for, motor oil or road salt, but they do not account for a rapid, repeated pH swing from highly caustic to highly acidic. Standard cable jacketing will just brittleize and crack under that kind of shock.
And the cleaning process itself sounds like a weapon against the seals.
It is. The requirement for frequent, aggressive IP6K9K washdowns is non-negotiable. We're talking 80 to 100 bar pressure. That's intense. And as with 80 degrees Celsius water. This high-pressure, high-temperature jet wash done daily or weekly is basically designed to find the single weakest point in every seal and every connector interface. A passenger car might see that once in its life. A cement mixer sees it every Tuesday.
Wow. And then finally, there's this unique challenge of grounding a structure that is designed to move on its own.
Yeah, the equipotential bonding challenge. You have this massive rotating mixer drum and its whole superstructure, and they're mounted on these big rubber dampeners to absorb vibration. Mechanically, that's necessary, but electrically, those rubber mounts are excellent insulators. But ISO 64693 is crystal clear. All conductive external parts have to be properly grounded to the vehicle chassis for personnel safety.
And what's the consequence if that grounding fails? I can guess it's bad.
It's lethal. If an internal HV wire chafes and faults to the metal drum and that drum isn't properly bonded, the entire drum becomes energized at 400 volts. Anyone touching the truck is at risk of lethal shock. So the engineer has to design a special, extremely robust braided ground strap to bridge that rubber-dampened gap. And the target is to ensure the drum surface maintains a resistance to the chassis ground of less than 100 million.
And that 100 million figure is critical because
Because it ensures any fault current returns so rapidly that it trips the main system fuse almost instantaneously, well before the danger threshold is ever reached.
this overwhelming set of unique requirements leads to what sounds like an absolute zero-tolerance mandate in the report.
It does. Based on the severe vibration profile alone, the engineering team has to immediately exclude all passenger car only HV connector platforms. They have to lock in LV215 vibration class 3 as the absolute validation baseline. For context, US KR2 is the standard for US passenger cars. LV215 Class 3 is specifically for agricultural, construction, and high-vibration engine environments. It demands much higher cycle counts, more aggressive stress profiles. It acknowledges the continuous, punishing world of the cement mixer.
All right, moving from those brutal requirements to the foundational physics. The first step is selecting the right wire diameter, and the report immediately warns against just using a cable supplier's rated current data. It says you have to reject vendor claims and rely strictly on the thermal equilibrium equation.
And that's because a vendor's rating is typically based on, a theoretical single wire in free air at a nice, cool ambient temperature, maybe 25 degrees Celsius. In a cement mixer's tight, hot chassis, that data is not just irrelevant, it's dangerous. A cable's true current capacity is fundamentally limited by its ability to shed heat. If heat generation exceeds heat dissipation, the cable temperature goes up, the insulation degrades, and eventually the system fails, often catastrophically.
And we have dual heavy loads here. The mixer drum motor rated at 80 kilowatts, peaking around 300 amps, and the drive motor rated at 120 kilowatts, peaking around 450 amps. These are not small numbers.
Not at all. And we have to account for the real-world conditions by applying 4 mandatory derating factors, or K factors, to that ideal current rating. If you fail to apply even one of these, the cable is undersized for the 15,000-hour life target, period.
Okay, let's detail those critical adjustments.
So first, there's a bundling factor. In commercial vehicles, cables run tightly packed in harnesses, bundles of 5, 10, or more. That dramatically reduces the surface area available for cooling. The report uses a conservative factor of 0.8 for the worst-case scenario. Second, pre-temp temperature derating. We have to assume the worst-case ambient temperature for the cable run. A chassis run might be 85 degrees Celsius. But the leads going into the inverter or near the diesel engine's exhaust components can easily hit 105. And that high temp immediately reduces the cable's ability to dissipate its own heat.
And the third factor addresses that longevity requirement.
Right, that's K10, which is typically 0.9, and it's required specifically for that 15-year lifespan target. It factors in the inevitable degradation of the system over time. Micro cracks in insulation, slight oxidation on the terminals, changes in material properties from all the heat cycling. Everything gets less efficient over 15 years, and you need a margin for that. And fourth, there's K-connector, which accounts for the contact resistance variability in the connections themselves.
Now, let's look at the specific hard numbers in the example. For that 300 amp peak load in a high vibration area, the current density calculation forces a massive safety margin.
Precisely. To mitigate the risk of heat failure that's accelerated by constant vibration, which increases localized resistance, the report mandates a maximum allowed current density of less than 1.8 amps per square millimeter. So you take 300 amps, you divide it by 1.8, and the minimum required copper cross-sectional area you get is 167 square millimeters. And since 167 isn't a standard size, that calculation immediately forces the engineer to specify the next available size up, a robust 185 square millimeter HV cable.
But wait, 167 square millimeters meets the physics on paper. Isn't mandating 185, which is nearly 10% larger, an unnecessary weight and cost adder? Where's the risk justification for that extra margin?
That margin is the definition of zero failure engineering in commercial vehicles. If you specify 167, you're relying on ideal conditions. The 185 square millimeter cable provides a crucial thermal buffer for all the unquantifiable future failures. Unexpected dirt and grease accumulation on the cable jacket, which reduces heat dissipation. Temporary voltage spikes, even slight manufacturing variances in the copper purity. In a commercial vehicle where downtime costs thousands of dollars a day, you sacrifice the small weight and cost savings for guaranteed thermal stability over 15,000 hours. The cost of a larger wire is nothing compared to the cost of a thermal runaway event.
That makes perfect sense. The extra size is basically just insurance against the real world. Okay, moving to insulation materials. We have a dual material strategy here based on mechanical strength versus thermal capacity.
Right. The primary choice is XLPE, or cross-linked polyethylene. XLPE is the mechanical hero. It offers superior abrasion, tear resistance, and excellent chemical resistance, which you need for that acid-alkali swing we talked about. It's rated to 150 degrees C, and it's the default choice for those long chassis runs, where it has to withstand the relentless impact of gravel and road debris.
But when you get close to a motor, you need more flexibility and higher heat resistance.
And that's where the high-performance silicone material comes in. It offers the highest temperature resistance, often up to 180 degrees Celsius. It's reserved for short, highly flexible runs, specifically near hot, high-vibration motors. But silicone's weakness is its low mechanical strength. It's easily scored or cut by sharp debris. Therefore, the report mandates a critical protection step, Any silicone-insulated HV cable must be protected by robust, high-strength braided sleeving to compensate for its vulnerability. It's a very surgical material choice, just specific hotspots.
That brings us to the connectors themselves. The report insists on a non-negotiable metal rule for any external connections.
This is a direct defense against those laws' blind spots. In this brutal environment, a plastic shell is labeled, and I love this phrase, of foreseeable failure mode. A piece of wheel-thrown gravel hitting a plastic housing at highway speed will shatter it, exposing the high voltage. Mandating metal shells for all external chassis connectors provides the necessary lifecycle defense, and critically, it also contributes to the continuous 360-degree electromagnetic shielding we'll get to next.
And the material that carries the current inside the connector, the terminal plating, that also has to be specified not just for current, but for 15-year resistance to micromovement.
For all high current interfaces, so battery to PDU, PDU to MCU, the design mandates silver plating. We're spending the extra money specifically to combat two failure modes that just wreck cheaper alternatives like tin plating, thermal runaway, and fretting corrosion.
Let's pause on fretting corrosion. We know it's caused by vibration, but what's the physical mechanism that makes it so catastrophic?
So think of two metal plates rubbing together constantly, but they're only moving by a few microns, smaller than a strand of hair. This microvibration causes wear, or fretting, on the contact surfaces. The tiny debris that wears off instantly oxidizes when it hits the air, creating these insulating particles of metal oxide. These non-conductive particles build up, and that increases the electrical resistance. That increased resistance generates localized heat, because P equals I squared R, and that heat accelerates the oxidation process, which further increases resistance, and you get this vicious cycle. Silver plating is just dramatically more resistant to this wear oxidation cycle than tin. It ensures that the low, stable contact resistance you need for high currents is maintained over 15 years and 15,000 engine hours.
This just confirms that every single choice here, from the cable gauge to the plating, is designed preemptively for failure modes that are totally unique to this machinery.
And that leads to the critical procurement requirement. Suppliers can't just provide data. They have to provide evidence of having mass-produced these specific connector platforms for at least 5 years in comparable heavy-duty applications. It's a risk mitigation strategy. Proven experience always trumps theoretical performance.
Okay, so once we have the physically robust core, we have to turn to the invisible challenge, managing electromagnetic compatibility, or EMC. The cement mixer presents this unique headache that the report calls the dual inverter noise problem.
That's right. The complexity comes from having two massive power electronic systems, the traction drive inverter and the mixer drum inverter, switching hundreds of amps at the same time using high-frequency IGBTs. All that switching generates this sharp, broadband electromagnetic noise. And when you have two high-frequency sources running together, they create complex interference patterns, specifically beat frequencies and harmonics that are notoriously difficult to filter out. And that noise can easily scramble sensitive low-voltage sensors.
And if the 24V sensors, which manage critical things like hydraulic pressure or gear selection, if they get corrupted, the VCU gets bad data. And that could lead to control logic errors, stalling, or worst-case runaway machinery. So we need a serious shield. What are the performance metrics?
We set really aggressive shielding effectiveness SE targets. For the low-frequency noise, which is dominated by the IGBT switching events, say 10 kHz to 30 MHz, we need at least 70 decibels of attenuation. For the higher frequencies, from 30 MHz to 100 MHz, we target at least 65 decibels. 70 decibels means the noise is attenuated by a factor of over 3,000 times. It's a lot.
So SE tells us how well the system blocks noise, but how do we physically measure the quality of the cable shield material itself?
That measurement is transfer impedance, or Z-dollars. This is the core physical measure the engineer has to demand from the supplier. Z-dollar measures how much noise current leaks through the shield or how much internal noise radiates out per meter of cable length. Think of the braided shield like a hose. You're not just testing for drips at the ends, you're testing how much water is soaking straight through the hose material itself.
And what's the specific target for that?
We mandate that Z-dollars must be less than $10 million per meter at 1 MHz. A lower impedance means the shield offers a much easier, continuous path for the noise current to travel, trapping it and shunting it back to the source before it can radiate out. Suppliers have to provide this specific Z-dollar curve, not just a simple compliance test.
And achieving that low impedance requires a strict mandate on how the shield is terminated, the 360-degree shielding mandate.
This is a clear condemnation of this engineering shortcut known as the pigtail method. If you just gather the shield braid and connect it using a thin wire led on one side, that thin wire introduces high inductance. At high frequencies, the exact noise we're trying to manage, that inductance acts like a choke. It effectively blocks the high-frequency current path and turns the cable into a giant, inefficient, radiating antenna. It's the worst thing you can do.
So the solution is to make the cable shield a continuous extension of the component casing itself.
Exactly. We mandate a 360-degree clamp, or ferrule, that connects the full circumference of the braided shield, which must have an optical coverage of at least 85% seamlessly to the connector's metal shell. This ensures a continuous, low-impedance electrical path that instantly shunts high-frequency noise from the cable jacket straight back to the motor casing or inverter casing, maintaining the integrity of the Faraday cage.
This requires us to be crystal clear on the distinction between the EMC system and the safety system. We have to separate church and state. EMC ground versus safety ground.
They have entirely different jobs and completely different physical characteristics. The EMC ground is a high-frequency path. Its only function is to return noise current rapidly to its source. Since high-frequency current travels on the surface of conductors, the skin effect, the path is primarily through the highest surface area of the cable shield and the metal housing, and it must be double-ended, connected at both the MCU and the motor to form a closed shielding loop.
And the life-critical safety ground.
That is the DC fault current path. Its function is life protection. In the event of an insulation failure, it has to rapidly carry hundreds of amps of DC fault current back to the PDU to trip the main fuse. This path has to be independent and extremely low impedance, and that's achieved with a separate, heavy braided ground strap. So while a shield needs to manage high frequency, the safety strap needs to manage high DC current, ensuring the resistance stays below 100 milliamps to minimize heat during a fault and maximize fuse tripping speed. They can't rely on the same physical path.
Beyond the electrical design, the physical layout of the harnesses is a primary tool for interference mitigation.
Right, we have three non-negotiable physical layout rules. First, separation. The HV, the 400-volt, and the LV, the 24-volt harnesses, have to be physically separated by a minimum of 200 millimeters when they run parallel. This distance is calculated to minimize capacitive and inductive coupling. Second, crossing. If that 200 millimeter separation is impossible, and they absolutely must cross paths, they have to do it at a near 90-degree angle. Crossing at a shallow angle maximizes mutual inductance and guarantees interference.
And for the inevitable sensitive 24-volt sensors that have to be located near the noise sources.
Filtration is essential. For any sensitive 24-volt sensor lines that run near the inverters, we mandate the use of common mode chokes, which are usually high-performance ferrite beads. These passively absorb the high-frequency common mode noise before it can corrupt the digital or analog sensor readings, making sure the vehicle control unit is always making decisions based on clean data.
We've established that this high-voltage system is fundamentally born for violence. So now let's focus on the physical durability, the armor required to survive 15,000 engine hours, starting with the mandatory entry ticket, IP6K9K.
This is the baseline, and we have to understand just how severe the test conditions are. 80 degrees Celsius water, jetting at 80 to 100 bar of pressure from 4 different angles. To pass this repeated, aggressive cleaning, the report defines a necessity for dual barriers in the sealing strategy.
Okay, walk us through those 2 lines of defense.
The first line is the single-wire seals. These are crucial because they prevent water from traveling along the slight gaps between the copper strands in the insulation jacket. If water wicks along the wire, that's capillary action, it can reach the terminal pins inside the connector body. The secondary defense is the peripheral seal. That's the large rubberized gasket that seals the entire mating face when the 2 connector halves click together. Both of those barriers have to be meticulously designed to withstand continuous thermal shock and extreme pressure without physical deformation or memory loss.
And beyond just water, we have to counter the unique chemical and physical attacks of the job site, specifically rejecting certain materials that fail that acid-alkali test.
Correct. The cable jacketing and conduits have to be tough. We're specifically mandating XLPE or polyamide, PA12 or PA6. We explicitly reject standard PVC. PVC's chemical resistance is just not sufficient, and under that alternating attack of strong alkali and strong acid, especially combined with temperature cycling, PVC undergoes rapid hydrolysis and brittleization. It leads to cracking and insulation failure. Polyamide, particularly PA12, offers superior resistance to both the alkaline solutions from the cement and the acidic cleaning agents.
And for physical protection against wheel-thrown debris, the report mandates a specialized dual-layer strategy for all chassis routing in high-impact zones.
This is truly armoring the system. The HV cable is protected by an inner PA12 corrugated tube. That's the primary barrier providing crush protection. But even PA12 can crack under a sharp stone impact. So this tube is then protected by an outer, self-closing braided sleeve. This sleeve acts as an armor layer. Its function isn't to stop penetration, but to disperse the impact energy over a wider area, much like chainmail, deflecting or cushioning the blow and preventing the sharp stone from concentrating all its force on one point of the inner conduit.
This brutal environment also mandates far more rigorous vibration endurance testing than standard road vehicles. The distinction here is crucial: frame-mounted versus motor-mounted.
Right, we use ISO 16750-3, but we differentiate the stress profile. For components that are mounted to the vehicle's frame, we use Test 7, which is random vibration, that simulates general road noise and potholes. However, for components mounted directly to the gearbox or the mixer drum motor, we have to use the far more aggressive Test 6, sign-on random vibration.
Okay, explain the difference. Why is sign-on random so much harder to pass?
Random vibration is just diffuse energy. It hits the component with a general shaking motion. Sign-on random combines that random road noise with specific high-frequency sine waves. Those sine waves mimic the highly predictable, resonant frequencies generated by the engine orders or the internal harmonics of that massive rotating mixer drum. By combining them, you force the components to continuously resonate at their most damaging natural frequencies while they're simultaneously enduring general road shock. This test truly accelerates failure modes.
And these tests can't just be performed at room temperature. You have to simulate each failure.
Absolutely. Reliability is only proven when you combine stresses. The vibration testing has to be sequentially combined with aggressive thermal cycling, the PTCE test, running from -40°C to 125°C repeatedly. This ages the material properties of the seals and plastics, causing them to harden or lose elasticity. And only then, when the seals are aged and brittle, do you subject them to the high-pressure IP6K9K spray test. This mimics the real-world scenario where a 5-year-old vehicle fails, not because the seal was weak on day 1, but because it lost its memory due to years of heat cycling.
Now let's look at the simple but brilliant installation rules that prevent failure even after all this successful testing.
First, the drip loop. This is pure, low-cost genius. Near every connector, the installed harness has to be designed to have an intentional downward U shape. This uses gravity to break the capillary action that draws water along the cable sheath. If you run a cable horizontally or uphill into a connector, water will wick right in. The drip loop ensures water collects at the lowest point and just falls away, preventing it from ever reaching the connector's primary seal barrier.
And the placement of the harness clamps is critical to prevent the vibration from destroying the electrical interface itself.
That's the optimized fixing. We have to decouple the mass of the heavy wiring harness from the delicate terminal interface. The first P-clamp, the critical fixing point, has to be placed approximately 100 to 150 millimeters away from the connector's back shell. This specific spacing acts like a shock absorber. Without it, the continuous vibration causes the heavy mass of the cable to lever the connector, inducing micro-movements on the terminals, which, as we established, rapidly leads to catastrophic fretting corrosion.
Finally, we have to talk about the non-standard validation test that just embodies this zero-failure mentality, the concrete bucket test.
This is the ultimate absurd reality check for the field engineer. The required test is to immerse a sample harness with the connector fully mated in wet concrete, wait 48 hours for it to cure completely, and then retrieve it, often requiring a hammer or high-pressure spray to free it. The mandate is that the seals, the lock mechanisms, and the external shell must remain structurally intact and functional. If the system can survive being encased in and violently extracted from cured cement, it proves its resilience against the chemical and compressive sources at the job site. It separates the rugged from the merely decorative.
All right, we shift now from pure mechanical survival to the life-critical domain of functional safety, which adheres strictly to ISO 26262. And the central nervous system of this protection scheme is the HVIL, the high-voltage interlock loop.
HVIL is a continuous low-voltage diagnostic circuit that runs in series through every single high-voltage connection point. The battery contactors, the charging port, all the major connectors. Its core operational logic is the safety maxim. Last mate, first break.
Explain how that physical sequencing works to save lives.
It's a brilliant piece of electromechanical design. The HVIL signal pins inside the connector are intentionally manufactured to be slightly shorter than the main power pins. When an operator begins to unplug the connector, the low-voltage HVIL loop breaks first, while the high-voltage power pins are still physically touching or are separated by a minimal gap. This immediate break signals the VCU or BMS to open the main contactors and initiate active discharge of the high-voltage bus capacitor bank.
What is the mandated response time for this life-saving reaction? I mean, we were talking about preventing a lethal arc.
The standard requires that from the instant the HVIL breaks, the system has to cut the high voltage and discharge the bus voltage to below 60 volts DC, which is the internationally recognized safety threshold, within a tiny window of 150 milliseconds. This rapid discharge ensures that by the time the exposed power terminals are physically separated far enough to create an air gap, there is insufficient voltage left to sustain a dangerous arc, which mitigates the risk of electric shock and fire.
The report insists that the HVIL system has to go far beyond a simple continuity check. We're moving into complex fault diagnosis here.
Exactly. Simple continuity checks are vulnerable to latent, dangerous failures. For example, if the HVIL wire chafes against the chassis metal and shorts to ground, a simple resistance meter might interpret that low resistance as a continuous, healthy loop. The system would then allow operation even though the interlock safety feature is bypassed. So the HVIL system, which is designed to an ACLB or C safety integrity level, has to be capable of diagnosing complex, latent faults, specifically distinguishing a deliberate disconnection from a short to ground or a short to HV plus power. This is usually done by introducing a supervisory voltage reference and monitoring the return voltage, ensuring the signal integrity matches the expected state.
In addition to the active HVL system, the report outlines these crucial layers of passive safety and mechanical interlocks, which fall under the concept of poka-yoke, or mistake proofing.
This is crucial for mass production quality and operator safety. First, we have mandated IP safety grades, even when the system is in use or being serviced. When the connector is unplugged, the socket plug halves have to be IPXXB, which means they are finger safe. When they're connected, they must be IPXXD wires safe, preventing small metallic objects or debris from being inserted and causing a short.
Then we have the physical locks that prevent poor assembly.
Dual assurance locks.
Yep.
CPA, connected position assurance, is that external physical slider, often molded in safety orange, that ensures the connector is fully seated, fully latched, and locked before the vehicle can be operated or the HV system energized. If the CPA won't physically slide into position, it means the mating process is incomplete, and that prevents a partial electrical connection that could overheat.
And the internal partner to the CPA.
That's the TPA, Terminal Position Assurance. This is an internal, secondary locking mechanism that ensures the individual metal terminals are locked into the plastic connector housing. This prevents the primary failure mode of terminal pushback during mating, which leads to poor contact, high resistance, and heat failure. All zero-failure high-voltage connectors have to use both CPA and TPA.
And to ensure instant visual identification for service and emergency personnel, there's the Universal Color Code.
Absolutely. It is a global mandate. All B-class voltage components, so anything above the 60-volt safety threshold, must be universally marked with RAL 2003 Safety Orange. This standardized color coding provides immediate, unmistakable visual warning to anyone approaching the vehicle during service or after an accident that lethal voltage is present.
So while the physical harness is often seen as a passive, sort of low-tech component, its design directly supports the highest safety goals of the vehicle.
Exactly. The harness itself is technically classified as ACLQM, quality managed, because it doesn't contain active logic. But its physical design, the thickness of the insulation, the metal shells, the integrity of the CPAP PA, that is the foundational barrier that enables the active safety system, the VCU or BMS, to meet its higher ACLD safety goals, like preventing lethal electric shock. If the physical component fails, the active system cannot guarantee the safety goal. And this is why functional safety engineers have to review and sign off on all HV harness designs, treating these passive components as active enablers of safety.
We've built the system, we've armored it, shielded it, and protected it with HVIL. The final stage is proving, beyond a reasonable doubt, that the design and the resulting production part will survive those 15,000 engine hours. This requires the Verification Test Plan, or DVP&R.
Right, and the report divides verification into two conceptually distinct but equally necessary stages: DV, design verification, and PV, product verification.
What's the fundamental difference in focus between proving the design and proving the product?
DV proves the design capability using prototype parts. It answers the question, is our theoretical design correct and capable of meeting the performance envelope? This includes initial clean tests, like withstand voltage, which is a 2150-volt DC insulation test, terminal retention, making sure it can take more than 110 newtons of pull force, and initial IP6K9K test on brand new seals. It validates the theoretical model before you commit to expensive tooling.
PV, on the other hand, deals with the rigorous, messy reality of mass production.
Yes, PV establishes mass production confidence. It uses final tooling parts and simulates years of operational wear. It answers the question, can we consistently build this product to the design specification, and will it survive the customer's entire duty cycle? This includes tests involving thermal shock, high vibration combinations, and crucially, full system-level validation.
The report makes the critical point that reliability is not proven by just passing individual tests. It's proven by combining stresses through sequential testing.
This is the non-negotiable step that separates serious commercial engineering from simple compliance. Passing IP6K9K on a brand new connector is easy. The goal is to replicate the aged failure scenario. For example, the test sequence might require subjecting the harness to 500 cycles of thermal shock to age the seals and plastics, then running it through 3 days of sign-on random vibration to stress the internal contacts and the P-clamps, and only then subjecting it to the 80-degree, 100-bar IP6K9K jet spray.
So the aged material and potentially compromised components are now exposed to the water intrusion test.
Exactly. If the seal fails the IP test after the thermal and vibrational wear, that is a true reflection of the product failing after 5 years in the field. This combined sequential stress test is the only way to expose latent failure modes that simple singular tests would just miss.
What are the two non-negotiable PV milestones that act as the final gate checks before production can even begin?
First is the 1,000-hour load cycle. This is a grueling, long-term current and temperature cycling test designed to ensure the stability of that silver-plated terminal interface. We're monitoring contact resistance constantly, and the report mandates that the resistance change has to be less than 5 milliamps throughout that entire 1,000-hour period.
Why is that 5 milliamp threshold so critical? It sounds absolutely tiny.
When you are running 450 amps through that circuit, even a tiny resistance increase becomes a major heat source. If the resistance goes up by just 10 milliamps, the power dissipated as heat, remember, P equals I squared R, it shoots up significantly. That heat accelerates fretting corrosion, and that leads to thermal runaway. The 1,000-hour test proves the long-term integrity of the plating and the constant force mechanism of the terminal itself.
And the final ultimate gate before the vehicle can roll off the line.
The report is crystal clear on this. No start of production, SOP, without passing vehicle-level IP6K9K validation. It is not enough to pass the test on a lab bench. A production intent harness, installed on the actual truck, routed with the necessary drip loops, clamped with the optimized fixing distances, exposed to the real chassis environment, it must prove it can survive the washdown. This tests the component in interaction with the vehicle, ensuring that installation errors or surrounding structure interference don't compromise the zero-failure design.
Looking across all these 6 highly rigorous stages, from designing the system to handle that acid-alkali alternation to proving its stability in the silent random vibration test, the engineering philosophy of this report is clearly a commitment to quality. It seems to be founded on 2 iron laws: always design for the worst case, and test like the customer, only harsher.
That most stringent overlay approach, and the willingness to oversize cables or mandate silver plating. It transforms component selection from a simple financial purchase decision into a proactive, life-saving engineering strategy. The engineers are building safety margins against chemical and physical threats that current global regulations haven't even really caught up to yet.
So for you, the listener, the core takeaway here is the necessity of checking the envelope conditions. You can't just rely on data sheets that assume typical values. If you're building any critical system, you have to define the thermal, the chemical, and the vibrational extremes that are unique to your application, and then design your components to survive those extremes with a healthy safety margin.
We've established that for these heavy commercial vehicles, the metal terminal is the heart, the braided shield is the skin, and the harness insulation is the artery. But considering the extreme wear, we should end with the true Achilles heel, the most difficult point to maintain over that 15,000-hour life. We address the challenge of the constantly rotating mixer drum and the requirement for low-resistance grounding to the chassis. We specified a static braided ground strap. But will a static braided strap, constantly twisting, vibrating, and exposed to cement slurry and high-pressure cleaning, truly survive 15,000 hours of dynamic stress and maintain that required less than 100 milliamp resistance? This raises a really important question. What dynamic grounding solution is necessary to truly eliminate that long-term fault path? Or is the engineer forever doomed to treat that ground strap as a critical high-frequency wear item that requires constant maintenance?